Here at Cape Canaveral, within minutes, this towering three-stage rocket will hurl another satellite into space for the United States. It is not the first. An impressive record of successful launches by this nation has been made. As the count continues, here is the background on a most important part of that successful history. Take a close look at the powerful first-stage booster. You will probably recognize it as the Air Force Intermediate Range Ballistic Missile, better known as Thor. Today, counterparts of this Thor are standing guard on overseas bases as an integral part of the free world's deterrent force in being. I'm Roy Neal, and this is the story of Thor. This will be our last report on Thor. The vigorous and extensive research and development program has been completed for some time now. Its product, a dependable weapon system, is being maintained on a fully operational status. Because of this, perhaps today's event, taking its place as it will among many successful launches, does not seem particularly important. But let me assure you it is. For this launch epitomizes one of the greatest technological achievements in the history of the world. Here in this control center, this blockhouse, we have men conducting an extremely complex launch operation as though it were a commonplace event. Well, for them, perhaps it is. We have progressed from theory to fact in such a short time, it's easy to forget the incredible amount of effort, the really remarkable achievements of the Thor program. Perhaps we could get a better perspective of the scope of accomplishments if we stopped for a moment and reviewed a part of that program. Let us recall the birth of Thor, and, as a matter of fact, the reasons leading to its conception. Like most war babies, Thor was conceived by international tensions. When the Russian bear came out of hibernation with a hydrogen growl, we needed a big stick, and we needed it fast. We had already begun development of 5,000-mile intercontinental ballistic missiles, but while the ICBM program was proceeding favorably, operational availability was still years away. We did have the immediate deterrent force of the Strategic Air Command, but how long could our bombers alone hold the Russian bear in check? The need was recognized for an intermediate-range ballistic missile capable of carrying a nuclear warhead. If agreements could be worked out with our allies, this missile could stand guard within easy retaliatory range. Specifically, the deterrent missile would have to be capable of placing a warhead on a pinpointed target 1,500 nautical miles away. Above all, it had to be ready as quickly as possible. This, then, was the groundwork for the beginning of Thor. The heightening world tension, the time it would take to develop extended-range missiles such as Atlas and Titan, and the geopolitical positions of our allies. But we had to have more than just a reliable missile. It would be worthless without the necessary equipment to support it, to maintain it and launch it. Useless without trained manpower. Futile unless provided in sufficient numbers to pose a timely demonstration of might. Traditionally, the procedure had been to develop the weapon first and then phase in supporting equipment as needed. In this way, there was no likelihood of making a costly mistake. If trouble developed, it was not too late to change the design. This procedure played it safe all right, but it also took 5 or 6 years, sometimes more. The men who conceived the IRBM did not have 5 or 6 years. Somehow, a new, faster approach had to be found, a way to compress time. This challenge was met with the concept of concurrency, preparing for the weapon's use while it was yet being developed. But if concurrency meant the saving of several years, it also meant running the risk of failure. There were many men who laid their careers on the line to get those years. If any one man could be called the driving force behind the concept of concurrency, it would be General Bernard A. Schriever, then head of the Air Force's Ballistic Missile Division. Although the concurrency decision had been a calculated risk, it is now a matter of history. how the Douglas Aircraft Company, working under Air Force and Space Technology Laboratory direction with a team of associated contractors, successfully designed, built, and test-fired the first Thor IRBM in just over 1 year. As for the vehicle itself, even in retrospect, it's still amazing. The scientific breakthroughs which were accomplished, which had to be accomplished in that year. In fact, there were so many, it's almost impossible to specify which of them made the greatest contribution to the missile design. Perhaps it was the unique waffle construction of the tank walls, which combined high strength with light weight. Or perhaps the revolutionary blunt nose cone developed by General Electric, which helped solve the re-entry problem. Perhaps the answer was not in the forming of aluminum, copper, and steel, but rather in the development by AC spark plug of the advanced guidance system necessary to impact the warhead precisely on the long-range target. But important as was this hardware development, the real story of Thor was in the boldness of the program decisions. For instance, the decision to freeze the missile design early in the program. The risk of this action is obvious. For how is it possible to invent on schedule? And how can men pioneer within fixed limits of time? In essence, freezing the design meant there was no room for a second guess. It meant the intensification of an already vigorous development and testing program. If there could be no going back to rectify mistakes, there could be no mistakes. Actually, the success of both the concurrency decision and the design freeze rested in the ability of the Air Force and the numerous contractors to function as a team, to design and manufacture right the first time, to test until there could be no doubt as to operational reliability. It meant construction of facilities while the components they would test were still on the drawing boards. Facilities such as the launch complexes, which were carved from the sandy Florida landscape at Cape Canaveral and from the folding hills of California's Vandenberg Air Force Base. In areas where missile development was ahead of new construction, existing facilities were pressed into service to bridge the gap. Most of these, such as the engine test stands at Edwards Air Force Base, were not designed for this new program, and the job of making them do was as much a test of human ingenuity and skill as it was a later test of missile hardware. But somehow, the rigorous testing program went on meeting an almost impossible schedule. When the new facilities at Sacramento, California were ready, they allowed a rapid expansion. For the first time, full-scale tests of the entire Rocketdyne propulsion system could be made while it was mounted in the vehicle. In the safety of steel and concrete, new experiments were conducted to speed weapon system reaction time to enemy attack. Wind and rain machines, for example, blasted the missile with the force of a small hurricane to see whether it would be ready to retaliate should the enemy strike under cover of a storm. At the same time, ground support equipment, such as mobile launch and checkout trailers, was being designed and fabricated. Transportation requirements were studied, and various methods worked out for eventual overseas delivery. Air Force crews were trained to service and launch the forthcoming missiles. This early training was complicated by the lack of completed hardware. For the first time in military history, combat crews started their training to maintain and operate a weapon before that weapon was even in existence. In anticipation of the imminent deployment of the Thor missile to overseas bases, Royal Air Force crews were brought to the United States for training. These men would maintain and operate the missiles stationed within the United Kingdom. Yes, there were many significant events in those early days of the program, but the very nature of the massive technological attack makes it difficult to single out clear-cut milestones. Certainly, the first attempted launch in January of 1957, just 13 months after the signing of a contract, was remarkable. It would be nice to be able to report that that first attempt was an unqualified success. Instead, the missile had just lifted from the pad when the lock start tank ruptured. This flight, however, could not be considered a total failure. Short as it was, the recorded data proved the basic missile concept to be valid. Thor, as a deterrent weapon system, could become a reality. And even while the fires of that first attempt were cooling, other Thors were being made ready. It was number 105 that accomplished the first fully successful flight. After that launch, we knew we were in the clear. There were setbacks, of course. Sometimes the problems seemed insurmountable, both the big ones and the small. But there were successes, too. And it wasn't long before the successes began to eclipse the so-called failures. Like the high acceleration flight of number 109, which pushed downrange more than 2,000 miles. Or the excellent performance of 113 with the new inertial guidance system. The first launch by an all-Air Force crew. The first launch by an all-British crew. The effectiveness of Thor was thoroughly demonstrated when it successfully delivered the warhead 1,500 miles downrange, where time after time it impacted with phenomenal accuracy on the precise target area. But more than accuracy and reliability was proved by these tests. They also demonstrated the courage and resourcefulness of the flight test crews. The intricate launch procedure did not always go smoothly, and many times it was only the spirit of dedicated men that carried the program through. One time, for instance, there was a power failure during a final countdown. Rather than call off the launch, the blockhouse circuit breaker was propped shut with a broom handle. For a while it was touch and go, but they got a successful launch. If an emergency developed on the pad during the countdown, it was often necessary to work near the fueled, armed, and as of then, unproved missile. The launch safety record is a tribute to the vigilance of the safety engineers, the scientists, and the flight test personnel. It was such men as these who proved Thor to be more than just a military weapon. Its versatility was first demonstrated in the spring of 1958. At that time, the Air Force needed a reliable booster to test a newly developed ablative nose cone at ICBM re-entry distances and speeds. Thus, the famous Thor-Able combination was born, with the Thor IRBM for the first stage and the Aerojet General liquid-fueled Able for the second. This combination eventually sent the nose cone more than 5,000 miles downrange with almost unbelievable accuracy. The first time re-entry was achieved with a full-scale nose cone at intercontinental speed and range. Subsequent recovery of a nose cone confirmed that the ablative technique could be successfully used under extreme re-entry conditions. Because of successes such as these, Thor was selected to be the United States' first double-programmed missile system. Even before the vehicle was declared operational as a military weapon, it had already been put in service for the exploration of space. It was logical and practical to turn the long-range Thor-Able vehicle toward the moon and the planets. Thus, the Air Force, operating under management of the Defense Department's Advanced Research Projects Agency, began the Pioneer Space Probe program. Except for the addition of a solid propellant third stage, few changes were required in the basic Thor-Able configuration. The result was the launching of Pioneer 1, a scientific payload which was sent more than 71,000 miles into deep space, the first penetration of its kind. Then followed the launching of Explorer 6, the paddle wheel satellite, which returned electronic pictures of the Earth from 17,000 miles in space. At Vandenberg Air Force Base, on the Pacific coast, Thor was pressed into service as booster for the Discoverer program. Again, the versatile Thor was fitted with another stage and payload, this one called the Agena. The record, as of mid-1960, 7 discoverers placed in polar orbit, each contributing to the nation's early warning and reconnaissance satellite programs, as well as to the Project Mercury Man in Space program. It would be difficult to measure fully the worldwide effect of the Tiros satellite, which was launched as part of the National Aeronautic and Space Administration's scientific program. But demonstrate it did that scientific research satellites such as Tiros can contribute immeasurably to the welfare of the world. The simultaneous launching of Transit, the Navy's navigation aid satellite, plus a radiation detection device, was another step in this direction. This was the famous piggyback launch of 2 satellites at the same time. Navigation from space, such as the Transit provides, will someday solve the ancient problem of pinpoint navigation anywhere on the face of the Earth. Meanwhile, Pioneer 5, the solar satellite, is whirling ever farther into deep space. We know even now that the information obtained from this one scientific achievement over a range of miles measured in the millions is changing the concepts of our solar system. These scientific achievements are almost monumental in their importance, but it's as an operational force of deterrence that Thor has had the greatest world impact. The establishment of Thor launch sites in the United Kingdom had a marked effect on military and diplomatic thinking. The accomplishment of this project, called Project Emily, will be regarded as one of the most difficult tasks of all time. Even in the early days of the program, everyone knew that establishing 4 complete missile squadrons on overseas bases was going to be a huge undertaking. The 4 squadrons were dispersed over 20 existing air bases and old World War II airfields. The actual work of constructing the bases was done by the British from blueprints supplied by the United States. Tolerances for this work were 1/8 of an inch, both in line and level. In addition, living quarters, both permanent and mobile, had to be constructed for the workmen as well as for the 1,000 RAF men who would make up the maintenance and launch crews of each complex. The Douglas Aircraft Company, again under Air Force direction, was given the responsibility of providing the design blueprints and of equipping the launch complexes as they were completed. This included installation of liquid oxygen and fuel storage and transfer systems, missile shelters, launch control trailers, erecting mechanisms, and maintenance and testing facilities. Since virtually all of the installation equipment was manufactured in the United States, overseas transportation had to be provided for tons of equipment and facility hardware. Rigid inspection and even more rigid schedules had to be met in spite of uncooperative weather. When the missile was ready, the complexes had to be ready, and it was as simple as that. And they were ready. Today, a new front line of defense stands poised for action in the United Kingdom. Manned by British crews, these missiles will never rise from the soil of England unless called upon for the supreme effort. But the real power of these weapons is not in the thunder of their engines. It is rather in the mere knowledge of their presence. Like the old wartime slogan, they also serve who only stand and wait.
Now, this launch. Routine, perhaps, might be the word for it. Another routine countdown by a Thor launch team. A launch which could just as well be conducted by our own Air Force, British RAF, or by Douglas aircraft missile men.
Yes, today Thor has a diverse capability, which marks it as one of the free world's most remarkable achievements, both on the military and scientific fronts. This fact is easy to forget, because now we have a tendency to take Thor for granted. And this, perhaps, is as it should be.
No, the Thor program management does not require detailed reports anymore. This will be the last, the final summary. But how do you explain the human energy that produced such a complex weapon and produced it in record time? A weapon which was conceived as an intermediate-range ballistic missile, but which has hurled its warhead more than 5,000 miles. A missile designed as a deterrent weapon to enforce the peace, but which performs as a scientific instrument for the conquest of space. So now it's over. And here's the scoreboard on a launch pad at Cape Canaveral. These symbols on this stand are an essential part of the story of Thor. They're more than mere symbols. They confirm the existence of an American spirit which many felt was dead. Here also are the reminders that horizons are not conquered without cost. The marks left by the first Thor that didn't fly very far. But this shattered nose cone from our first launch attempt is not a symbol of defeat. Rather, it is a silent source of inspiration for the time to come when we may have another big job that seems just as impossible. A scorecard on a launch pad at Cape Canaveral. Part of the record of the tangibles, the hardware. But what of the intangibles? Perhaps only history can tell. We do know that today, Thor is standing guard in distant parts of the globe, its very presence taking the sting out of enemy threats, however wild. We do know that time can be beaten, that engineering, production, training, testing, and operation can be conducted in a concurrent program that is well worth the risk. Thor has shown us that all missiles have a great expanding potential, and that the national role in space can provide valuable information for peace as well as for defense. And Thor has proven that competitive industrial contractors can work hand in hand for the common good. And above all, it has proven that there are still dedicated pioneers in this free nation, and that the combined efforts of these men can transcend the challenges of the impossible.